Welcome to the session on functions and graphs, solving modulus problems. The objectives for this session are to use a combination of transformations with mod f of x and f of mod x and apply ideas relating to domain and range to solve problems. The inverse of a function carries out the reverse operation to the original function. Elements in the range of the original function are mapped back into the elements of the domain of the original function. Therefore, inverse functions only exist for one-to-one functions. The inverse of f of x is written f inverse of x, as shown on your screen. Functions f of x and f inverse of x are inverses of one another. The graphs of y equals f of x and y equals f inverse of x are reflections of one another in y equals x. Let's illustrate this. Suppose we have a function y equals f of x as shown. Then the inverse function is a reflection in the line y equals x, as shown on the screen. The domain of f of x is the range of f inverse of x. So, for example, as you can see on the graph, there is a point 0, 3 on the line y equals f of x. This is reversed in y equals f inverse of x. So, the point 3, 0 is on the line y equals f inverse of x. And similarly for the point minus 6, 0, or equivalently 0, minus 6. The range of f of x is also the domain of f inverse of x. We're now going to give a summary of transformations, and then we'll use these transformations of a function f of x to sketch graphs of more complex transformations. F of x plus a is a translation by the vector minus a, 0. F of x plus a is a translation by the vector 0a. F of minus x reflects f of x in the y-axis. Minus f of x reflects f of x in the x-axis. F of ax, where a is a constant, is a horizontal stretch of scale factor 1 over a. A times f of x is a vertical stretch with scale factor a. Now let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. Given the function t of x equals 2 mod x minus 3 plus 1 for x in the real numbers, sketch the graph of this function and state its range. So let's solve this. We begin by sketching y equals mod x. Clearly, this isn't the function that we're looking for, but it is going to start to help us in stages lead to this function. So here's a sketch of y equals mod x. The line y equals mod x minus 3 is a translation by the vector 3, 0. And y equals mod x minus 3 looks something like this. The next stage is to stretch y equals mod x minus 3. The line y equals 2 mod x minus 3 is a stretch of scale factor 2, as shown here. And finally, y equals 2 mod x minus 3 plus 1, which is the function we're looking for, is a translation by vector 0, 1, as shown here. So this is our function. We are now going to take a look at the range. Now t of x equals 2 mod x minus 3 plus 1 is greater than or equal to 2 times 0 plus 1. This is because the smallest value that mod x minus 3 or any modulus function can take is 0. And of course 2 times 0 plus 1 is equal to 1. Therefore, the range of t of x is y in the real numbers with y greater than or equal to 1. And now for part B. Given the function t of x equals 2 mod x minus 3 plus 1 for x in the real numbers, solve the equation t of x equals x over 4 plus 2. So let's solve this. Solving this equation gives us 2 mod x minus 3 plus 1 equals x over 4 plus 2. We begin by sketching this. So 2 mod x minus 3 plus 1 equals y looks like this, and y equals x over 4 plus 2 is mapped on top of this and looks something like this. We are looking for the intersection points of the two functions, or the intersection points of the two sides of the equation. These intersection points are denoted by point A and point B, as shown in the graph. At A, the line has been reflected for the modulus function, and therefore we're looking to find the intersection point of 2 times minus x minus 3 plus 1 with x over 4 plus 2. And expanding the brackets inside the brackets and multiplying the equation through by 4 gives us this expression here. And expanding the brackets which are left over gives us this expression. And finally tidying up gives us x equals 20 over 9. At point B, the modulus function is not reflected, and therefore we leave x minus 3 as it is. And so we have this equality. Multiplying through by 4 gives us this expression here, and expanding the brackets gives us this expression. And finally we can tidy up to solve for x, and this gives us x equals 4. So at A, x is 20 over 9, and at B, x is 4. And now for another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. The function f is defined as f such that x is mapped to 4 minus mod 3x plus 2 for x in the real numbers. we are required to specify the range of f. So let's solve this. We're going to begin by sketching the function. This isn't actually required for the question, but it will give us a feel for what we're required to do. So here's our sketch. Now f of x equals 4 minus mod 3x plus 2. In order to find the smallest or the largest value of this function, we need to look at the smallest or largest value of mod 3x plus 2. Therefore, f of x is less than or equal to 4 minus 0, because mod 3x plus 2, or any modulus function, has a minimum value of 0. And therefore, f of x is less than or equal to 4. Therefore, the range of f is y in the real numbers with y less than or equal to 4. And now for part B. The function f is defined as f such that x is mapped to 4 minus mod 3x plus 2 for x in the real numbers. We are required to explain why f inverse does not exist. So again, here's a sketch of the function. And let's solve this problem. Notice that several values of x are mapped to one value of y. In this example, it's actually two values of x mapping to one value of y. In either case, the function f is therefore many to one. And this is why f inverse does not exist. And now for part C. The function f is defined as f such that x is mapped to 4 minus mod 3x plus 2 for x in the real numbers. We are required to solve the inequality f of x is less than 2. So let's solve this. We begin with a sketch to get an idea of the problem. We have y equals 4 minus mod 3x plus 2, and superimposed on that is y equals 2. We're going to begin by solving f of x equals 2. In other words, we're going to solve 4 minus mod 3x plus 2 equals 2. The equality occurs at these 2 points shown in the graph here, A and B. These points are crucial because when x is less than the value at the point A and when x is greater than the value at point B, we have the required inequality. In other words, f of x is less than 2. However, when the x value is between the points A and B, we have f of x is greater than 2. Let's begin with point A. At A, we have this scenario here. 4 minus 3x plus 2 is equal to 2. We've removed the modulus signs because we know that the modulus part of the graph is reflected at point A. And then we tidy up, expand and solve. To give x equals minus 4 over 3. And now for B. At this point we have 4 minus 3x plus 2 equals 2. We've removed the modulus signs, but we've left 3x plus 2 as it is, because it's not the reflected part of the graph. And so tidying up and expanding the brackets gives us that x equals 0. So at point A, x equals minus 4 over 3, and at point B, x equals 0. So f of x is less than 2 in the regions x less than minus 4 over 3 and x greater than 0. X less than minus 4 over 3 is this region here, as indicated on the graph with the arrow, and x greater than 0 is this region here. This brings us to the end of this session. If you have understood its contents, you should be able to use a combination of transformations with mod f of x and f of mod x and apply ideas relating to domain and range to solve problems. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.